Hey everyone, you know that feeling when you're staring at a math problem and you just can't solve for x? Well, it turns out some of the most important equations in science and engineering are exactly like that. They don't have a nice, clean answer. Today, we're going to dive into the super clever methods mathematicians have come up with to hunt down those unfindable solutions, one step at a time. Let's get into it.
Seriously, how do you do it? It's kind of like trying to untangle a hopelessly knotted rope with just one hand. Your standard algebra toolkit is great, but sometimes the knot is just way too complex. So what do you do when you hit that wall? That's the exact question we're going to tackle.
Okay, so look at this. On the left, you've got a simple straight line problem. Easy peasy, x equals 2, no sweat. But that function on the right, oh man, that thing is a wild ride. There is no simple way to just rearrange it and find where it hits 0. And this is where we have to totally shift our mindset from solving an equation to searching for a solution. So here's our game plan. First, we're going to define what we even mean by a root. Then we'll explore 3 awesome methods for finding them, each one with its own personality. And finally, we'll wrap it all up by figuring out how to pick the right tool for the job. All right, first things first. When we say we're solving something like f of x equals 0, what does that actually look like? What is this root thing that we're so obsessed with finding? It's actually super simple. Visually, a root is just the spot where the graph of our function crosses the horizontal x-axis. That's it. At that one exact point, the value of the function is 0. Our entire mission is to find that x-coordinate. Okay, let's kick things off with the most intuitive method of them all, the bisection method. Now, it's not going to win any speed contests, but it is incredibly reliable. Think of it as the tortoise in this little mathematical race. The big idea here is actually beautiful in its simplicity. You start by trapping the root inside a range, and then you just squeeze. You just keep cutting that range in half, over and over again, getting closer and closer to the real answer with every single step. So here's the play-by-play. First, you find a range where you know the root has to be, because the function is, say, negative on one side and positive on the other. Then you guess the dead center, the midpoint. You check the value there, and based on that, you throw away half the interval where the root can't possibly be. And then you just do it again and again, zeroing it on the solution. Let's actually try this. We've got a root hiding somewhere between 1 and 2. So our first move, guess the midpoint, 1.5. Now we just plug that into our function to see if we've overshot or undershot our target. Okay, turns out the root is actually between 1.5 and 2, so we can just toss out that whole first half of our range. Our next guess is the new midpoint, 1.75. And just like that, our search area is half the size it was a second ago. We're closing in. So here's the key takeaway for this one. This method is what we call linearly convergent. All that really means is we cut down our error by a fixed amount, in this case by half with every single guess. It's slow, it's steady, but you know what? It's a sure thing. It will find the root. The bisection method is solid, for sure, but just chopping the interval in half every time feels a little, well, blind, doesn't it? It doesn't pay any attention to the shape of the function at all. So that begs the question, can we make a smarter guess? Oh yeah, we can. This is where the secant method comes in. Instead of blindly picking the midpoint, this method actually looks at the function's values to make an educated guess. It uses the steepness of the curve to literally take aim at where it thinks the root is going to be. So here's how it works. The method takes 2 points on our curve and draws a straight line, that's a secant line, right between them. Our next guess isn't the midpoint anymore. Nope, it's where that secant line smacks right into the x-axis. It's a much more targeted shot. So how much faster are we talking here? Well, its rate of convergence is about 1.618, which, and this is so cool, is the golden ratio. This is called superlinear convergence. It means that unlike bisection, which just kind of plods along, this method actually gets faster and faster as it gets closer to the answer. It's a huge upgrade in speed. But we can do even better. If you're willing to bring out the big guns, and by big guns I mean calculus, you can use what's often the fastest, most powerful method of them all, the Newton-Raphson Method. Okay, so remember, the secant method needed 2 points to draw its aiming line. But what if we could draw an even better line, a more accurate line, using the information from just a single starting point? Is that even possible? This is the magic of the Newton-Raphson method. By using the function's derivative, which is just a fancy way of saying its exact slope at one specific spot, we can find the tangent line at that point. We then just follow that tangent line all the way down to the x-axis and bam, that's our next guess. And it is incredibly accurate.
The speed of this thing is called quadratic convergence, and this is where it gets kind of insane. What this means, in plain English, is that with every single step we take, the number of correct decimal places in our answer roughly doubles. Yeah, doubles. It is ridiculously fast.
Of course, there's always a catch, right? This incredible power and speed comes at a price. To even use the Newton-Raphson method, you have to be able to calculate the derivative of your function, and sometimes that's really hard, or maybe even impossible to find.
So we've looked at 3 totally different ways to solve these problems. It's best to think of them as different tools in a numerical toolbox, right? I mean, you wouldn't use a hammer to turn a screw, and you wouldn't always reach for Newton-Raphson either.
This little table sums it up perfectly. Bisection is your dependable workhorse. It's slow, but it is guaranteed to get the job done. The secant method is your go-to for a major speed boost, especially when you don't know the derivative. And Newton-Raphson, that's the high-precision power tool you break out when you need absolute maximum speed and accuracy. And look, this isn't just some abstract math theory. These iterative methods power everything from your phone's GPS to complex financial models and weather forecasts. They prove that even the most massive, daunting problems can be cracked one intelligent guess at a time. It kind of makes you wonder, doesn't it? What other huge problem could we solve if we just took it one small step at a time?